Welcome to the deep dive. Today we're really plunging into quite a fascinating and you could say provocative research paper. It's from NVIDIA Research and the Georgia Institute of Technology.
Right.
And it's titled, pretty boldly I think, Small Language Models Are the Future of Agentic AI.
It definitely catches the eye.
It does. So our mission for this deep dive is really to unpack the core argument of this paper. It fundamentally challenges what feels like the prevailing wisdom in AI right now.
The bigger is always better.
Exactly. That larger models are always, unequivocally the way to go.
Yeah.
We're going to explore why, despite these massive investments and, frankly, the widespread adoption of large language models, or LLMs, the paper suggests the future of AI agents might actually hinge on their smaller, more specialized counterparts. It's a bold claim, and, well, we're here to see what backs it up and maybe what it means for you.
It's a really crucial discussion, I think, especially given how quickly AI agents are popping up across, well, nearly every industry you can imagine.
Right.
And this paper isn't just like making a casual observation. It lays out a pretty compelling case that could, as you said, fundamentally shift how we think about, the operational models, the economics of AI.
Okay.
Get ready for some, I think, surprising facts and a genuinely fresh perspective on what intelligence, quote unquote, truly means in practical deployed AI systems. It really challenges our assumptions about just scale.
Okay, let's definitely unpack this. Before we dive into the whole small is mighty argument, we probably need to set the stage a bit, understand the current landscape.
Sure.
Agentic AI is, it's clearly on a meteoric rise. But first, maybe just quickly, what exactly are we talking about when we say AI agent, just so we're all on the same page?
Yeah, good point. So when we talk about AI agents in this context, we're defining them as software entities that have a degree of agency.
It's agency, right.
Because it means they're not just, executing pre-programmed commands. They're actually capable of making strategic decisions using various tools pretty effectively, breaking down complex tasks into smaller, manageable subtasks.
Right.
And performing some quite sophisticated reasoning. For action planning, problem solving, they're sort of deliberating and acting autonomously, but within, defined parameters. It's a big leap beyond just traditional software.
That makes sense. So they're like little digital assistants, but with kind of brains of their own. And this growth you mentioned, it's not just theoretical, right? The paper gives some numbers. What are some of the most compelling stats that really show how fast the sector is growing?
Oh, the adoption rate is genuinely striking. Recent surveys highlighted in the paper, they show that over half, more than 50% of large IT enterprises are already using AI agents in some capacity.
Wow, okay, over half.
Yeah. And remarkably, a full 21% of those enterprises adopted them just last year.
Just in the last year.
Just in the last year. So this isn't some future trend. It's a massive, tangible shift happening right now.
That adoption rate alone, that really underlines a significant trend. What about the money side? Is there real capital flowing into this? Because hype is one thing, but investment is another.
Absolutely. There's this growing expectation, both from users and the market itself, that AI agents are going to play a really substantial, maybe even transformative role in the modern economy. And this isn't just buzz. The financial commitments are already, frankly, staggering. The paper mentions that as of late 2024, the agentic AI sector had already pulled in over $2 billion in startup funding.
Per billion.
Just in startup funding. And its valuation stood at around $5.2 billion. With projections, and this is where it gets wild, seeing it balloon to nearly $200 billion by 2034.
$200 billion.
$200 billion. These figures, they clearly signal a deep, deep economic commitment to this technology. It's not just a flash in the pan.
That is a massive trajectory. Okay, so AI agents are here. They're growing incredibly fast, huge amounts of capital flowing in. But who's actually powering these agents right now? It feels like, as we said, large language models are the undisputed champs currently.
That's right.
What are the financial implications of this setup, according to the paper? I think you mentioned some staggering numbers earlier.
You're absolutely right. LLMs, the models like GPT-4o or Claude 3.5, they are fundamentally the core components. They provide that foundational intelligence for most modern AI agents. They're brains, if you like.
Right.
Enabling agents to understand, reason, act. And typically, an AI agent works by communicating with these LLMs. It
Right.
makes requests to their API endpoints, which are almost always hosted on centralized cloud infrastructure.
So the agent sends a query to this huge brain in the cloud.
Exactly.
And gets instructions back.
Okay.
And this operational model, it seems incredibly entrenched in the industry right now. The paper really highlights the significant financial commitment here. It said the market for the LLM API serving just providing the answers was estimated at what, $5.6 billion in 2024.
Yeah, around $5.6 billion. That's for the service itself.
But here's the kicker, right? The investment into the hosting cloud infrastructure needed to run these massive models that surged to a staggering $57 billion in the same year.
$57 billion.
Yeah.
That is a huge difference, a tenfold difference.
It truly is a tenfold discrepancy between the market size for the services, the APIs, and this colossal investment in the underlying infrastructure to provide them.
So why the gap? Why accept that?
Well, this huge gap has largely been accepted because the industry has been operating under this assumption, this belief, that the centralized LLM model will just remain the cornerstone without any major changes.
Right.
The belief is that this massive upfront investment will eventually deliver returns, comparable to traditional software or internet solutions, probably within 3 to 4 years.
Okay.
And this deep industry commitment, the huge financial bets placed on this specific model, that is exactly what the paper we're diving into today challenges head on. It's looking at this legacy approach, this assumption, and saying, hang on, is this actually the right way forward? Right. Okay, so the paper sees this LLM dominance, but then it really challenges that whole paradigm. It argues, defends the position that small, not large, language models are the future for agents. This is where it gets really interesting. But first, definitions are key here, I imagine. What do they actually mean by small versus large? Because that can change pretty fast in AI.
Yeah, definitions are absolutely crucial to avoid confusion. Because what's small today might have seemed huge just a few years back.
For sure.
So the paper gives these really pragmatic working definitions. The first one, working definition 1, WD1, it says an SLM, small language model, is basically a language model that can fit onto a common consumer electronic device.
Like a phone or laptop.
Exactly. And perform inference, generate responses with sufficiently low latency to be practical when it's serving the agentic request of just one user.
That's a great way to put it. Very practical.
Yeah.
Focuses on the utility, the accessibility for a single user, not just raw numbers or parameter counts. So it's about real-world deployment on your device with quick responses. That sounds like a different way of thinking than just bigger is better.
It really is. And then, logically, working definition 2, WD2, defines an LLM as simply any language model that is not an SLM by that first definition.
Okay. Simple enough.
And they do give a rough guideline. They note that as of 2025, they're comfortable considering most models below, say, 10 billion parameters in size to be SLMs. But the key thing about these definitions is their focus on practicality, maybe even timelessness.
How so?
They avoid tying the definition to specific hardware metrics like FLOPs or exact parameter counts, because those things become obsolete so quickly.
True.
Instead, they ground the definition in the practical goal: deploying capable models on widely available consumer devices, serving users nearby with low latency. This really captures the core motivation behind training SLMs in the first place, getting capable AI that can run locally or on a much tighter budget.
That makes a lot of sense. It shifts the focus from just abstract size to tangible, user-centric performance. Okay, so with those definitions clear, what's the paper's foundational statement about SLMs? What's their main contention here?
Their core contention is framed as these three, I think, quite powerful value statements. They argue that SLMs are, first, V1, principally sufficiently powerful to handle the language modeling tasks required by agentic applications.
Okay, so that they can do the job.
Right. Second, V2, they are inherently more operationally suitable for use in agentic systems than LLMs.
More suitable in practice.
Exactly. And third, V3, they are necessarily more economical for the vast majority of language model uses in agentic systems, simply because they're smaller. Cheaper. And based on these three views, the paper makes that firm statement: SLMs are the future of agentic AI.
That is a strong declaration, and they use that phrase necessary consequence, not just a suggestion. What makes them so certain? Is there some deeper reason they're hinting at beyond just cost savings or efficiency?
Yeah, the phrasing is definitely deliberate. It's not framed as a recommendation like you should do this or an obligation. It's a statement of what they see as a necessary consequence if you follow natural priorities, like efficiency, cost, long-term sustainability. The paper argues that shifting to SLM-first architectures isn't just some technical or economic tweak. It actually promotes a more responsible, more sustainable path for AI deployment overall.
Ah, okay.
It's about proactively dealing with these skyrocketing infrastructure costs and, frankly, the environmental concerns that come with constantly scaling up ever larger LLMs. So this perspective suggests that embracing SLMs is maybe a step towards a more economically sound and resource-efficient AI future. It connects to that humane and moral ought idea mentioned in the outline. It's the practical, sensible thing to do.
This brings us to a really key point then. Why is the current dominance of LLMs in agentic AI considered excessive and misaligned if they're so incredibly powerful? I mean, big models have done amazing things. Why knock them?
Well, the paper asserts that while LLMs absolutely offer impressive generality and, great conversational fluency, the reality on the ground is different. The majority of agentic subtasks in deployed systems are actually quite repetitive, highly scoped, and often non-conversational.
Right, like filling out a form or booking a flight. Specific things.
Exactly. And for those types of tasks, the most important requirements are things like efficiency, predictability, and low cost. In that context, SLMs don't just suffice. The paper argues they are often preferable.
Preferable, okay, why?
Because they offer distinct advantages.
Yeah.
Lower latency, significantly reduced memory and computational needs, and substantially lower operational costs. And critically, they do all of this while maintaining perfectly adequate task performance within those constrained domains.
So it really is about matching the tool to the task. You wouldn't use a giant industrial crane to lift a pencil, even if the crane is incredibly powerful.
That's a perfect analogy. It reminds me of how we've always specialized tools. Why should AI be any different? We don't use a bulldozer to plant a single rose, right?
Right.
Even if it could theoretically do it.
Right.
This pragmatic view of language model use within agentic architectures is really central to their argument. These agent systems are designed to break down complex goals into modular subtasks. And for each of those subtasks, a specialized or fine-tuned SLM can handle it reliably. The paper argues that insisting on using LLMs for all these simple subtasks reflects a misallocation of computational resources. It becomes economically inefficient and, at scale, environmentally unsustainable.
And this leads them to push for something they call heterogeneous agentic systems. That sounds a bit technical. What does that actually mean in practice? How would that look?
Yeah, heterogeneous just means made of different parts. In these systems, SLMs would be used by default for the vast majority of routine specialized tasks. The grunt work, essentially. Then the big LLMs are invoked selectively, sparingly, reserved only for situations where you really need that truly general reasoning ability or maybe open domain unconstrained dialogue.
So you mix and match.
Exactly. This modular composition lets you combine the precision and efficiency of SLMs with the broader generality of LLMs when needed. You can build agents that are both highly cost-effective and remarkably capable. It's about smart resource allocation, not just brute force power.
Like having an LLM as the general manager overseeing things.
Yeah.
But all the specialized departments like accounting, sales, logistics are handled by these super efficient SLMs.
That's a great way to think about it. It mirrors how complex systems often work in the real world.
Okay, now that we've got the core position down, let's dive into the 7 specific arguments the paper lays out to support this claim. Argument 1, A1, is a big one. SLMs are already sufficiently powerful for use in agents. This really challenges that common perception that smaller models just can't cut it on capability.
Yeah, this is a critical pillar supporting their first value statement, V1, that SLMs are principally sufficiently powerful. And it's true, over the past few years, the capabilities of SLMs have advanced incredibly significantly.
More than people realize.
I think so. While scaling laws still generally hold bigger models are usually more capable overall, the curve, the relationship between model size and capability is becoming much steeper. Meaning the capabilities of newer SLMs are getting much, much closer to those of previous generation LLMs. Well-designed SLMs are now meeting and sometimes even exceeding performance levels that we used to think only much larger models could achieve.
And the paper gives some specific examples, right, which is super helpful.
Yeah.
Can you highlight maybe 1 or 2 where these smaller models are really punching above their weight class?
Absolutely. Take, for instance, Microsoft's Phi series. Their Phi 2 model, which is tiny at just 2.7 billion parameters.
Yeah, okay.
It achieves common sense reasoning and code generation scores on par with models 10 times its size, like 30 billion parameter models. It runs about 15 times faster.
15 times faster?
Yeah. And then more recently, their Phi 3 small at 7 billion parameters, is rivaling 70 billion parameter models from the same generation in things like language understanding, common sense reasoning, code generation.
Wow.
And we're seeing this pattern across the board. NVIDIA's Nematron H family, models around 2 to 9 billion parameters, they offer instruction following and code gen accuracy comparable to dense 30 billion LLMs, but using just an order of magnitude fraction of the inference compute power, the FLOPs.
So way cheaper to run.
Way cheaper. Or look at Hugging Face's small M2 series models, as small as 1.7 billion parameters, performing on par with 14 billion contemporaries in tool calling and instruction following. It's genuinely astonishing how quickly these smaller models are catching up in raw capability.
What's truly amazing here, and it feels like a massive shift, is that we're moving past just counting parameters. It seems the real constraint for AI agents isn't just how big the model is anymore, but maybe how cleverly we train and augment even these smaller models.
That's a great way to put it.
This fundamentally changes the game for practical, deployable AI. And beyond their sort of out-of-the-box performance, the paper also mentions ways to boost SLM capabilities at inference time, right, when they're actually running. What are those techniques?
Yeah, they highlight several useful techniques. One is called self-consistency. Basically, the model generates multiple possible responses to the same prompt and then checks for agreement among them. It's like cross-referencing itself to improve reliability.
Okay.
Another is using verifier feedback, where maybe a separate, simpler system evaluates the quality or correctness of the SLM's output and asks it to try again if needed. And critically, tool augmentation. This is a big one. They mentioned Toolformer, a 6.7 billion parameter model that was shown to outperform the massive 175 billion parameter GPT-3 on certain tasks.
Oh.
Simply by intelligently using external APIs, it learns when to call out to other tools like a calculator or a search engine to get information instead of trying to store and reason about everything internally.
So it uses the web, basically.
Sort of, yeah. Or other specialized tools. And similarly, they mentioned studies where models as small as 1 to 3 billion parameters have rivaled much larger LLMs on complex math problems by using structured reasoning techniques, breaking the problem down step by step in a structured way.
Okay, so the key takeaway here seems to be that capability isn't just about size anymore. It's about training, architecture, and how you use the model within an agentic system.
Exactly. With modern training methods, clever prompting, and these agentic augmentation techniques, the binding constraint for many agent tasks is now capability, not simply parameter count. SLMs are proving they can supply sufficient reasoning power for a huge portion of agentic invocations. This makes them not just viable, but arguably more suitable than LLMs for building modular, scalable, and cost-effective agent systems.
That is a really powerful first argument. It definitely challenges that bigger is always better mindset. Okay, let's move to argument 2A2. SLMs are more economical. This sounds like it directly tackles that huge tenfold cost discrepancy we talked about earlier between API revenue and infrastructure spending.
It absolutely does. This argument really hammers home the significant benefits SLMs offer in terms of cost efficiency, adaptability, and deployment flexibility. And all of these are incredibly valuable in agentic workflows, which often require a lot of specialization and ongoing iterative refinement.
So how do these savings actually show up in practice? Where does the money get saved?
Well, firstly, and most obviously, in inference efficiency. It's just running the model day to day. Serving a 7 billion parameter SLM can be anywhere from 10 to 30 times cheaper.
10 to 30 times.
Yeah, it's a huge range depending on the specifics, but significant savings. Cheaper in terms of latency, so faster responses, cheaper in energy consumption, and cheaper in FLOPs, the raw computational power needed.
Okay.
This massive cost reduction is what enables real-time agentic responses at scale, which is often crucial. Plus, the paper mentions advancements like NVIDIA Dynamo, which are systems explicitly designed to support high-throughput, low-latency SLM inference, both in the cloud and potentially on device.
And it's not just the running cost, but managing the hardware too.
Exactly. Because SLMs often require less, or sometimes no, parallelization across multiple GPUs or compute nodes compared to giant LLMs, the ongoing maintenance and operational complexity of the serving infrastructure also comes down significantly. Fewer moving parts, less to go wrong, cheaper to manage.
That's a huge operational cost saving right there. That sounds like the day-to-day running. What about the development side, like tuning these models for specific jobs? Is that cheaper too?
Yes, and that brings us to the second point, fine-tuning agility. There are these techniques called parameter-efficient fine-tuning, or PEFT. Common ones are LoRa and Dora.
Right, PFT, heard of those.
What they let you do is adapt a pre-trained model to a new task by only training or modifying a very small fraction of its parameters, not the whole massive thing.
Okay.
For SLMs, using PAFT requires only a few GPU hours of compute time. This means you can literally add new behaviors, fix bugs, or specialize an agent for a new task overnight, maybe even within hours.
Compared to weeks for an LLM.
Exactly. Compared to potentially weeks or even longer and much higher cost for retraining or heavily fine-tuning a large LLM. This accelerates development cycles dramatically and cuts down the time to market for new agent capabilities. That's a massive business advantage.
Definitely. And you touched on running AI on your own device, edge deployment. That idea is really appealing, especially for privacy and speed.
Right.
Is that actually becoming feasible with SLMs?
Absolutely. This is where edge deployment becomes a real possibility. Advances in on-device inference systems, the paper mentions NVIDIA Chat RTX as an example, are demonstrating the capability for local execution of SLMs directly on consumer-grade GPUs, like the one in your gaming laptop.
Wow.
This offers real-time offline agentic inference, which means inherently lower latency because there's no round trip to the cloud, and much stronger data control and privacy because your sensitive data never has to leave your device.
That's huge. Imagine a truly private AI assistant processing your emails or documents right there on your machine.
It's a very compelling vision.
You also mentioned something about parameter utilization. It sounded a bit technical, but what's the core idea? Is it like how efficiently the model uses its brain power?
Yeah, that's a good way to think about it. It relates to how much of a model's total brain power, its parameters, is actually engaged or active when processing any single input.
Okay.
Studies suggest that LMs, despite their enormous size, often exhibit what's called sparse signal processing. This means only a small fraction of their parameters might be actively involved in generating a response for a given input.
So a lot of it is just sitting idle.
Potentially, yes.
Yeah.
For many operations, a large portion of the parameters might be dormant, essentially just taking up memory and energy without directly contributing to that specific output. In contrast, this sparse behavior seems to be less pronounced in SLMs.
Interesting.
This suggests that SLMs might be fundamentally more efficient in how they utilize their parameters. A larger proportion of their smaller brain is actively contributing to the task at hand. They're more all in on what they've got, you could say.
So it's not just having fewer parameters overall, but potentially using the ones they have more effectively. All these economic points seem to converge on this idea of modularity, right? Building with smaller specific parts instead of one giant monolith.
Precisely. The paper uses that nice analogy of a Lego-like composition of agentic intelligence. Instead of trying to scale up one single monolithic model to do everything, you scale out by adding small, specialized expert SLMs for different tasks. This approach yields systems that are inherently cheaper to run, faster to debug because the modules are simpler, easier to deploy, and crucially, better aligned with the operational diversity needed by real-world agents that perform many different kinds of tasks. When you combine this modular SLM approach with smart tool calling, caching results, and fine-grained routing to direct tasks to the right specialist, these SLM-first architectures really do appear to offer the most promising path forward for cost-effective, adaptable, and sustainable agentic AI.
That takes us really neatly into argument 3A3. SLMs offer greater flexibility. This seems to build directly on that modularity idea we were just discussing.
It is, yeah. Because they're smaller and so much cheaper and faster to train or fine-tune, SLMs are just inherently more flexible than the big LLMs when you integrate them into agentic systems.
And how does that flexibility translate into practical benefits?
Well, it directly translates into affordability and practicality when you need to train, adapt, or deploy multiple specialized expert models for all the different routines an agent might need to perform.
So businesses using these agents could respond much more quickly to changing needs. If a regulation changes or a customer asks for a new feature.
Exactly. That's a huge competitive advantage. This efficiency enables really rapid iteration and adaptation. It makes it genuinely feasible to address evolving user needs quickly. Like you said, supporting new behaviors, meeting new requirements for output formats, or maybe complying with changing local regulations in specific geographic markets.
Right.
Imagine being able to update your agent's compliance behavior for a new privacy law overnight. Literally, rather than waiting weeks or months for a massive, centralized LLM to be retrained and redeployed globally. That's potentially game-changing, especially for regulated industries like finance or healthcare.
Definitely. And there's a broader societal benefit mentioned here too, something about the democratization of agents. How does SLM flexibility contribute to that idea?
This is a really interesting and potentially significant consequence. The argument is, when it becomes cheaper and easier for more individuals, smaller companies, researchers, maybe even hobbyists, to participate in developing and deploying language models for agentic systems, then the overall population of agents becomes more likely to represent a wider, more diverse range of perspectives and societal needs. You get AI built by more people for more purposes.
And that diversity helps how?
Well, that diversity, in turn, can help reduce the risk of systemic biases creeping in, which can happen if only a few large organizations are building all the models. It also naturally encourages greater competition and innovation in the field. With more actors entering the arena to create and refine models, the pace of advancement could accelerate significantly.
Kind of like the explosion of apps we saw when mobile development tools became widely accessible.
It's a fantastic analogy. This could potentially do something similar for AI agent development, making it much more widespread and diverse.
That's a powerful potential impact. Okay, let's move to argument 4A4. Agents expose only narrow LM functionality. This feels like it pushes back against the idea that bigger models are better because they, know everything.
Right. This argument suggests that an AI agent, in practice, functions as a kind of heavily instructed and externally choreographed gateway to the underlying language model.
What does that mean, choreographed gateway?
It means the agent has a specific user interface, maybe a chat window or some controls, and a selection of tools it can use. And when these are engaged correctly by the user or the agent's own logic, they perform something useful. But from this perspective, even a super powerful generalist LLM, one that was engineered for incredibly broad capabilities, is ultimately restricted. It's constrained by the carefully written prompts the agent sends it and the meticulously managed context it's given. It's forced to operate within only a small, specific slice of its vast potential skill set for any given agentic task.
So even if the LLM could write a sonnet or explain quantum physics, the agent's design might only ever ask it to, say, extract an email address from a block of text.
Exactly. It's like having a master chef capable of creating Michelin star meals, but you only ever ask them to make scrambled eggs every single time.
Okay, got it.
Therefore, the argument goes, a small language model, if it's appropriately fine-tuned just for those specific narrow prompts the agent actually uses, would be entirely sufficient to do the job.
And cheaper and faster.
And cheaper and faster, more flexible, bringing all those benefits we discussed. The vast generalist understanding of the LLM isn't actually being fully utilized in that narrow context, making it overkill. You're essentially paying for a supercomputer to do basic arithmetic.
That sounds like it directly addresses that alternative view we'll get to later, the one saying LLMs are always superior due to general understanding. Okay, let's park that for now and look at argument 5A5. Agentic interactions necessitate close behavioral alignment. This sounds like it's about making sure the AI speaks the right language to other computer systems it works with.
Precisely. This point highlights the very practical nuts and bolts demands of agent-to-code interactions. A typical AI agent is constantly interacting with code. Either the language model itself is making calls to external tools, like APIs, or the model is returning output that needs to be parsed and understood by another piece of the agent's own code.
Right.
For these interactions to work smoothly and reliably, it's absolutely essential that the generated tool calls and the output from the model conform to very strict formatting requirements.
So we're talking about things like structured data formats, JSON or XML for tool calls, or maybe a specific markup like Markdown or YAML for the outputs. It has to be precise, character perfect sometimes.
Exactly that. The order of parameters, their data types, the specific keywords expected by a tool's API, or the precise structure expected by the code that's consuming the LLM's output, all these dictate very specific formats. For example, tool calls might absolutely need to be in XML or YAML or Markdown or maybe even LaTeX for documents. And in such scenarios, it becomes kind of unnecessary, even undesirable, for the model to be able to handle lots of different formats. Usually just one specific format is chosen and enforced for consistency across that particular agentic application. You need it to stick to the script.
And a big general-purpose LLM, while powerful, might occasionally hallucinate or just drift slightly from that strict format, maybe adding an extra comma or forgetting quotes, causing errors downstream in the system.
That's the core issue here. That could be disastrous in a fully automated workflow. It's highly undesirable for the model to make these occasional, perhaps statistically rare but still possible, hallucinatory mistakes and respond in a format different from what the code parts of the agent expect.
Right.
Because of this critical need for reliability and predictability in format, the paper argues an SLM that's specifically trained with a single enforced formatting decision, maybe baked in during its post-training or added through quick, low-cost fine-tuning, is much more preferable in the context of AI agents compared to a general-purpose LLM that might get it right most of the time.
Because most of the time isn't good enough for automation.
Exactly. The SLM ensures predictability and reliability, which are paramount for seamless automation. Again, a specialized tool is simply better and safer for a specialized job requiring precision.
Okay, argument 6A6 touches on the architecture of agents again. Agentic systems are naturally heterogeneous. This sounds like it loops back to that idea of mixing and matching different model types, the Lego-like system.
Yeah, this argument builds on that concept and also on the idea that a language model itself can actually be a tool called by another language model.
Ah, okay. Layers of models.
Right. Or similarly, every single time an agent's controlling code decides to invoke a language model, it has the flexibility, at least in principle, to choose any available language model endpoint based on the specific need at that moment.
Mm-hmm.
So the paper argues that incorporating multiple language models of different sizes and capabilities, designed for queries or operations of varying levels of complexity, offers a very natural and efficient way to introduce SLMs into the system. It's not an all-or-nothing choice.
So instead of one single giant brain trying to juggle everything from simple data extraction to complex strategic planning, you could have this network of specialized brains, each doing what it's best and most efficient at.
Precisely. You could imagine various scenarios. Maybe you have a powerful LLM acting as the root agency, the main orchestrator or planner.
The manager again.
The manager, yeah. While subordinate SLMs handle the more routine, high-volume, or specialized subtasks like parsing documents or generating standard reports, or you could even have an agent comprised entirely of specialized SLMs. Maybe one fine-tuned just for handling the conversational interface with the user, another specifically optimized for carrying out certain controller-defined language tasks related to the agent's core function, and perhaps another SLM dedicated just parsing specific data formats very reliably.
Right.
This kind of heterogeneity allows for optimal resource allocation. You use the right size tool for each job. It leads to tailored performance for each specific part of a complex workflow. And frankly, it reflects how complex real-world systems are often built. Lots of specialized components working together, not usually one single monolithic entity doing everything.
That's a really compelling architectural vision. Okay, finally, argument 7A7. Agentic interactions are natural pathways for gathering data for future improvement. How does this connect specifically to SLMs, and what's the sort of so what for someone building or using these agents?
This argument really ties into the operational suitability and the economics again. As we've discussed, agentic applications often involve very careful prompting. The prompts are designed to focus the language model on delivering very narrow, specific functionality at any given moment.
Right, the choreographed gateway idea.
Exactly. Each of these carefully prompted invocations, if it's handled correctly by the system, is itself a natural source of high-quality training data for future improvement, assuming, of course, that you're careful about not retaining confidential or private data inappropriately.
So the very act of the agent doing its job creates the data needed to make it better and potentially cheaper over time. That sounds like a built-in feedback loop.
It is. It's a fantastic built-in feedback loop. A system can be designed to sort of listen in on or decorate the interface where tools or models are called. By doing this, it can gather highly specialized instruction-following data pairs. Here was the specific narrow prompt, and here was the successful response, or tool call. This data, which is generated organically through normal use, can then be used to fine-tune an expert SLM specifically for that narrow task, the goal, to eventually replace the expensive LLM call for that task with a cheap SLM call.
Ah, so you use the LM initially, gather data on how it handles a specific task, and then train an SLM to do just that task more cheaply.
Precisely. The paper argues this is enabled by the very architecture of agents and produces this stream of high-quality, highly relevant data. You could even post-filter this data by looking at the overall success of the agent's workflow. Only keep the examples where the agent successfully completed its goal.
Right, so you're training on success.
Training on success. This makes the production of these expert SLMs, designed to stand in place of LLMs for specific subtasks, a natural and integrated step in the agent deployment lifecycle. It's not just some auxiliary effort you might do later. It becomes part of the operational process. It creates this powerful, virtuous cycle. Use the agent, gather data, train SLMs, reduce costs, improve efficiency, repeat. The system gets smarter and cheaper with every use.
Okay, those 7 arguments make a really strong case for SLMs. But, no good research paper ignores the other side. The paper acknowledges and then tries to rebut several significant alternative viewpoints, the skeptic's case, if you will.
Right, and it's important they do.
Let's start with alternative view 1, AV1. LLM generalists will always have the advantage of more general language understanding. This seems to directly dispute the operational suitability, the V2 value statement of SLMs. And I can see why people would think this. LLMs do seem incredibly versatile and knowledgeable.
Yeah, this is probably the most common gut reaction, the most popularly cited belief against using SLMs, especially when you only need to perform a narrow language task. This view basically says, look, a big LLM will always outperform a small SLM on any given language task, simply because it has a broader understanding of the world and language itself. It's just generally smarter.
Right. And this view relies on 2 main counterarguments, correct? What's the first one, the one about scaling laws?
The first one, counterargument 1, or CA1, it posits that there's just substantial empirical evidence out there showing the superiority of LLMs over SLMs from the same generation when it comes to general language understanding. They acquire this broad understanding naturally as they scale up, following well-established scaling laws. Their larger scale, the argument goes, enables them to demonstrate better performance across a huge array of specialized natural language tasks, text generation, translation, reasoning, you name it. They claim LLMs outperform SLMs even when those smaller models are trained specifically for those tasks. To claim otherwise, critics would say, is basically to contradict these fundamental, well-documented scaling laws.
Seems plausible.
Yeah.
And the second counterargument, CA2, brings up something intriguing called a semantic hub. What exactly is that supposed to be?
Yeah, CA2 suggests that LLMs possess this hypothesized mechanism, a semantic hub. The idea is that this hub allows them to integrate and abstract semantic information, meaning from various different modalities like text, images, code, and languages in a very generalized way. The theory is that this hub lets LLMs generalize knowledge across different languages and domains far more effectively than smaller models could. The same study suggests SLMs lack the capacity or scale to develop such a complex internal hub.
So the conclusion is?
The conclusion drawn is that while SLMs might be efficient for narrow, specific tasks, their limited scale fundamentally restricts their ability to achieve the same deep level of general language understanding because they lack this internal mechanism for complex abstraction. Therefore, the argument concludes, LLM generalists would always retain a performance advantage in agentic applications because that general understanding is always beneficial, even for specific tasks.
Okay, those are pretty strong claims, backed by scaling laws and this semantic hub idea. How does the paper rebut these? It sounds like a fundamental disagreement, especially with the scaling law argument.
It is a fundamental disagreement, and the paper offers several rebuttals. First, regarding CA1 and the scaling laws, rebuttal A8 points out something crucial. Popular scaling law studies often assume that the model architecture stays the same within a generation as you scale up.
Ah, okay. They just make the same design bigger.
Exactly. But recent work, especially on SLM training, demonstrates distinct performance benefits when you consider using different architectures that are better suited for different model sizes. This suggests that simply scaling up the same monolithic architecture isn't necessarily the only or even the best path to superior performance. It's not just about getting bigger. It might be about getting smarter in the design, tailoring the architecture to the scale.
So it's not just size, but also clever design specific to that size. That's a critical nuance they're highlighting.
It's a very critical nuance. Then rebuttal A9 brings the flexibility of SLMs back into the picture, which we talked about under argument 3. A small language model can be easily, cheaply, and quickly fine-tuned for a specific task to perform at the desired level of reliability. This crucial factor, the ability to rapidly and affordably specialize in SLM, is often completely unaccounted for in those broad scaling law studies, which typically just evaluate generalist performance out of the box. You're not comparing like if one model can be quickly molded for a specific job and the other is just a generalist.
That makes sense. And what about the cost? Even if you can fine-tune an SLM to be reliable, does that cost negate its economic benefit compared to just using the already reliable LLM?
That's addressed by rebuttal A10. It argues that reasoning, or more generally, scaling up the compute used at inference time, test time compute scaling, is significantly more affordable for SLMs. Meaning, while an SLM retains its benefits like being agile and deployable across devices, you can reasonably expect to scale up the compute you throw at it during inference. maybe running it multiple times with self-consistency checks, or using more complex decoding strategies to reach the desired level of reliability for a specific task without incurring prohibitive costs. Doing the same kind of inference timescaling with a massive LLM would be far, far more expensive. So you can afford to make the SLM reliable.
Okay. And finally, that semantic hub argument from CA2. If LLMs really have this unique internal structure for generalization, how do they counter that?
Rebuttal A11 tackles the semantic hub idea head-on. The paper argues that the utility of such a hub, if it exists, primarily shows itself when the tasks or the inputs being processed by the language model are highly complex and require integrating diverse information.
Right.
However, as we discussed under argument 4 and 6, advanced agentic systems are typically designed, or at least actively prompted, to perform decompositions. They break down complex problems and inputs into smaller, simpler pieces. Therefore, the argument goes, the actual invocations of SLMs within these well-designed agentic systems would be focused on these appropriately broken down subtasks. And these subtasks are often so simple that any potential benefit from a general abstract understanding gained from a semantic hub would be minimal, perhaps even negligible, in terms of practical utility for that specific step. The complexity is handled by the agent's overall orchestration and planning logic, not necessarily by every single individual model invocation.
So you're not relying on the SLM to solve the entire grand, complex problem, just one small, manageable piece of it, where general understanding isn't the bottleneck.
Exactly. The agent structure itself mitigates the need for that deep, generalized understanding at every single step.
Okay, that effectively breaks down that first alternative view. It shifts the focus from raw general intelligence to how that intelligence is actually applied and needed within the specific structure of an agent. Let's move to alternative view 2, AV2. Centralization makes LLM inference cheaper overall. This disputes the economic benefit, the V3 value statement of SLMs. It argues that the sheer economy of scale you get from running giant centralized LLMs dwarfs any per token cost savings from smaller models. It's basically saying, sure, a single SLM inference might be cheap, but can you really run billions of SLM inferences across many specialized models as cheaply as running one giant efficient LLM service?
Yeah, this view is essentially arguing that despite the clear per token or per inference cost benefits of SLMs, the overall business reality of deploying AI models at massive scale means centralized LLMs are still more cost-effective due to these powerful economies of scale.
Yes.
It's the classic argument of, say, a single large factory being inherently cheaper per unit produced than many small dispersed workshops.
Makes intuitive sense. What are the main counter-arguments from this perspective that the paper addresses?
The first one, CA3, states that it's simply more difficult to fully utilize the compute capacity and properly balance the incoming load for an inference endpoint serving a highly specialized expert SLM compared to one serving a generalist LLM.
Why is that?
The idea is that a single versatile LLM can handle a wide, unpredictable range of requests, making it easier to keep the expensive GPU servers busy and therefore more cost-effective per unit of infrastructure. A specialized SLM might sit idle more often if requests for its specific task aren't constant.
Okay, utilization challenges. And the second counter-argument, CA4, points to other costs, maybe hidden costs of managing all these individual SLMs.
Yes, exactly. CA4 highlights that the costs associated with the initial setup of inference infrastructure, combined with the significant ongoing costs of acquiring and retaining the specialized engineering talent needed for its upkeep, are often conveniently omitted in simple per-inference cost calculations.
Right.
These infrastructure and talent costs, the argument goes, would become much more prominent and burdensome if the deployment and management of numerous specialized SLMs became the responsibility of many individual agent service developers in a more decentralized model. The complexity of managing hundreds of SLMs might outweigh the inference savings.
So how does the paper respond to this viewpoint? Do they just dismiss it? Because it sounds like a very valid, practical concern, especially for large organizations.
No, they actually don't dismiss it at all. They acknowledge AV2 as a valid case-specific viewpoint. They state quite candidly, and I think refreshingly, that regarding the overall systems-level economics, the jury is still out. It's a complex equation with many variables.
Okay, so they concede it's debatable.
They concede it's debatable, depending on the specific context and scale. However, they also present several factors that suggest the economic benefits of SLMs might still prevail in many, if not most, agentic scenarios. Rebuttal A12 points to recent and ongoing improvements in inference scheduling software and the modularization of large inference systems. Again, they mention things like NVIDIA Dynamo.
Right.
These advancements offer unprecedented levels of flexibility in managing workloads within large monolithic computing clusters. This directly counters the traditional stance expressed in CA3 that specialized SLM endpoints are inherently hard to keep utilized efficiently. Essentially, the tools for managing and efficiently running many smaller, diverse models within shared infrastructure are getting much, much better.
So the tech is catching up to manage the complexity?
The tech is catching up. And what about the setup and talent costs mentioned in CA4, the barrier to entry for a more decentralized approach?
Rebuttal A13 addresses that. It notes that the most recent analyses looking at the setup costs of infrastructure indicate a consistent falling trend. This is happening due to underlying technological reasons, hardware getting cheaper and more powerful, better open source management tools, etc.
Okay. This suggests that the barrier to entry for setting up and managing SLM-specific infrastructure is decreasing over time, making a more distributed or specialized model approach progressively more feasible, even for smaller players. So while AV2 raises valid points about current system complexities, the technological and cost trends seem to be moving in favor of making SLM deployment more economical overall.
Okay, that makes sense. Finally, we have alternative view 3, AV3, the head start of LLMs. This view suggests that, look, maybe both SLM-centric and LLM-centric agentic worlds are equally possible in theory, but the reality is the LLM world has a considerable head start. Due to existing deployment practices, all the optimization work already done, and simple industry inertia. This feels like the most human, most pragmatic objection of all. It's just easier to stick with what's working now.
It truly is the most pragmatic objection, and the paper acknowledges this straightforwardly as a distinct possibility. It's a realistic recognition of the current situation. Massive investments have already flowed into the LLM paradigm. Infrastructure is built around it, engineers are trained on it, and the industry naturally gravitates towards what's already established, optimized, and understood. There's a powerful inertia at play, absolutely. It's like trying to turn a giant supertanker around quickly.
But they don't just throw up their hands and say, well, LLMs win because they got there first, do they? They must still have some optimism if they wrote this whole paper arguing for SLMs.
Not at all. Despite acknowledging this significant head start and the power of inertia, the paper maintains its core position. It argues that the cumulative weight of all those arguments we discussed earlier, A1 through A7.
Right, the power, the economics, the flexibility.
Exactly. The sufficient power, the superior economics for most tasks, the greater flexibility, the fact that agents often only need narrow functionality, the critical need for strict behavioral alignment, the naturally heterogeneous structure of agents, and those built-in data-gathering pathways for continuous improvement. They believe the combined force of these fundamental advantages can plausibly overturn the current state of affairs.
So they think the underlying benefits are strong enough to overcome the inertia.
They believe the fundamental advantages of SLMs for agentic applications are just too compelling to ignore in the long run. They argue that practical priorities and economic realities will eventually drive the shift towards SLM-first architectures, even if it takes time to overcome the current LLM head start. The economics, they essentially argue, will eventually win out.
Okay, that sets the stage for the next part. If the arguments for SLMs are so compelling and can potentially overcome inertia, why aren't they already more widely adopted right now? The paper identifies several practical hurdles, barriers to SLM adoption that exist today. What are these main roadblocks?
Yeah, the paper points to three primary barriers that are slowing things down. The first one, B1, is exactly what we just touched on.
Okay.
The large upfront investment that has already been sunk into centralized LLM infrastructure.
Right, the sunk costs.
As we discussed in the intro, these huge capital bets have been placed on centralized LLMs being the dominant paradigm for providing AI services. As a direct result, the industry has moved much faster to build tools, platforms, and infrastructure specifically tailored to that model, largely overlooking or deprioritizing the development of infrastructure for more decentralized SLM deployment or efficient on-device inference. It's a classic case of existing investments shaping future development pathways.
That makes perfect sense. It's just hard to pivot when you've already spent billions building the highway in one direction. What's the second barrier they identify?
Barrier B2 relates to the use of generalist benchmarks in SLM training, design, and evaluation. Historically, much of the research and development work on SLMs has kind of followed in the footsteps of LLM design. This means focusing on the same broad generalist benchmarks that LLMs are often judged by things like standardized language understanding tests, general knowledge quizzes, etc. However, the paper highlights a crucial point. When you shift the focus and evaluate models solely based on benchmarks measuring their agentic utility, how well they actually perform specific practical tasks within an agentic workflow, SLMs often easily outperform larger generalist models on those specific tasks, especially after fine-tuning.
Ah, so we might be measuring them by the wrong yardstick.
In many cases, yes. This suggests a misalignment between how SLMs are commonly evaluated using broad, general benchmarks and their true potential and strengths when applied to the specific, often narrow tasks required by agents. We're essentially asking them to ace a general knowledge final exam when their real strength lies in highly specialized vocational skills needed for the job.
That's a great analogy. Okay, so evaluation methods are a barrier. And the third one?
Barrier B3 is perhaps simpler, but still significant. Just a general lack of popular awareness. SLMs, frankly, often don't receive the same level of intense marketing buzz and press attention that the giant LLMs do.
True, everyone knows the big names.
Exactly. LLMs capture the headlines because their impressive generalist capabilities are easy to demonstrate and understand. They can chat, write poems, answer trivia. The benefits of SLMs, cost savings, efficiency for specific tasks, flexibility are perhaps less flashy, even though they might be more important for many industrial and business scenarios. So it's partly a visibility problem. The smaller, specialized workhorses often fly under the radar compared to the headline-grabbing giants.
But the paper seems optimistic that these are hurdles, not insurmountable walls, right? They emphasize these are practical issues, not fundamental flaws in SLM technology itself. How do they see these barriers being addressed or falling over time? Is there light at the end of the tunnel for SLM adoption?
Yes, definitely. The authors are clear that these are practical hurdles, not reasons why SLMs can't be the future. For instance, barrier B1, the inertia from those large upfront investments in LLM infrastructure, is already being reduced. As we mentioned, advanced inference scheduling systems like NVIDIA Dynamo are providing much greater flexibility in how large compute clusters allocate resources, making it easier to efficiently run diverse workloads, including specialized SLMs on shared infrastructure.
So the infrastructure is becoming more adaptable.
Exactly. Barrier B2, the issue with using only generalist benchmarks, is also gaining increasing recognition within the AI research and development community. We're starting to see more focus on developing agentic-specific benchmarks and evaluation methods that truly reflect the practical utility of models in these contexts. This will better highlight the strengths of SLMs where they excel.
Okay, so the evaluation metrics are evolving.
They are. And barrier B3, the lack of popular awareness, well, the paper expects that to fall naturally over time. As the significant economic benefits and operational advantages of deploying SLMs in agentic applications become more widely known, demonstrated, and experienced by businesses,
The word will get out.
the word will get out. Economics usually speaks loudly. They don't put a specific timeline on it, of course. But the argument is that the underlying technological trends, and crucially, the compelling economic forces are steadily moving in favor of SLMs, making a broader shift seem almost inevitable in the long run.
That's a hopeful outlook. And speaking of concrete paths forward, the paper doesn't just diagnose the problem or make predictions. It actually proposes a specific practical algorithm for converting existing LLM-centric agents to a more SLM-first architecture. This sounds incredibly valuable for any developer or organization looking to actually make this shift. It's not just theory, it's a how-to guide.
It absolutely is. The paper outlines a 6-step algorithm, which they argue provides a relatively painless migration path for agentic applications, from relying solely on LLMs to leveraging specialized SLMs. It recognizes that the very nature of these agentic apps, their modularity, their task-specific invocations, makes them inherently suitable for eventually switching from using expensive LLM generalists to cheaper SLM specialists at many of their internal interfaces.
Okay, let's walk through these steps. This sounds really useful. What's the very first step, S1, for someone wanting to try this conversion process?
Step S1 is secure usage data collection. This is absolutely foundational. It involves deploying instrumentation, basically logging tools, to record all the non-human computer interaction calls the agent makes to the LLM.
So not the user chat, but the internal calls.
Right. The internal calls the agent makes to the LLM for reasoning, planning, tool use, etc. You need to capture the input prompt sent to the LLM, the output responses received, the content of any tool calls the LLM decided to make, and optionally, things like latency metrics for each call, which can help target optimizations later.
Okay, log everything the agent asks the LLM to do internally. How do you do that securely?
That's critical. The recommended best practice is to set up encrypted logging pipelines. Access to the logs should be strictly controlled using role-based access, and very importantly, all data should be anonymized with respect to its origin before it's stored. You need to ensure user privacy and data security are paramount right from the start.
Okay, so essentially you're recording a detailed, secure diary of exactly how the current LLM is being used in its internal agentic role. What's next once you have that raw data?
Step S2 is data curation and filtering. Once you've collected a sufficient amount of log data, the paper gives a rule of thumb of maybe 10,000 to 100,000 examples being a good starting point for fine-tuning small models.
Okay, 10K to 100K examples.
Right. Once you have that, it's absolutely necessary to meticulously clean it. You need to remove any PII, personally identifiable information, PHI, protected health information, or any other kind of application-specific sensitive data that could potentially cause a data leak if it were used to train a new SLM specialist model.
How do you do that reliably?
There are popular automated tools available for dataset preparation that can detect and mask or remove many common types of sensitive data, like names, addresses, credit card numbers. For more application-specific sensitive inputs, like internal company documents or legal text, the paper suggests data can often be automatically paraphrased. This means rewriting the text to obfuscate specific named entities and numerical details while still preserving the general informational content needed for training. The goal is to make the data safe and clean to use for training new models.
That's a crucial step for privacy and security, definitely. Once the data is clean and anonymized, how do you figure out which specific tasks within the agent are suitable for an SLM? How do you decide what jobs the smaller models should take on?
That leads directly to step S3, task clustering. This involves using unsupervised machine learning techniques, specifically clustering algorithms, on the collected prompts and the corresponding agent actions, the LLM responses or tool calls.
Okay, group similar requests together.
Exactly. You're looking for recurring patterns. These clusters are crucial because they help you identify and define the candidate tasks that are being performed frequently and might be suitable for SLM specialization. The granularity of these task clusters will depend on the specific agent, but common examples might include things like recognizing user intent from a short phrase, extracting specific data fields from an invoice, summarizing meeting notes in a standard format, or generating code to call a specific internal API. You're basically finding the most frequent repetitive jobs that an SLM could potentially handle very well.
So you identify the specific repetitive task the LLM is doing, then presumably you need to pick the right SLM for each of those tasks from the growing number of options out there.
Precisely. Step S4 is SLM selection. For each distinct task you identify through clustering, you need to select one or more candidate SLMs that seem like a good fit. The criteria for selection here are important. You need to look at the SLM's inherent capabilities. Does it generally follow instructions well? Does it have decent reasoning abilities for the complexity needed? What's its context window size? Its performance on relevant benchmarks? How does it score on tests that measure performance on tasks similar to the one you identified? Example, code generation benchmarks if the task is coding. Its licensing. Is it permissible for commercial use if needed? Are there restrictions? And its deployment footprint. How much memory and computational power does it actually require to run? Can you realistically deploy it? This is where you leverage all those advancements in SLMs we discussed earlier, like the Phi series, Nimbotron, etc., selecting a model known to excel in the specific constrained domain relevant to your task.
Okay, makes sense. Once you have the clean data for a specific task and you've chosen a promising candidate SLM, the next logical step is actually training or adapting that SLM. I imagine that's where the fine-tuning comes in.
That's step S5, specialized SLM fine-tuning. For each selected task and its corresponding SLM candidate, you prepare a task-specific dataset using the curated and filtered data you gathered in steps S2 and S3. Then, you fine-tune the chosen SLMs on these specialized datasets.
And they recommend PFT again here.
Yes. Parameter-efficient fine-tuning techniques like LoRa or QLoRa are highly recommended here. Why? Because they significantly reduce the computational costs and memory requirements associated with the fine-tuning process, making it much more accessible and affordable. These techniques, remember, allow you to adapt the model effectively by only adjusting a tiny fraction of its parameters, saving enormous amounts of compute power and time compared to retraining the whole model.
Right. Cheaper, faster tuning.
Exactly. Of course, if you have the resources and need the absolute maximum adaptation for a critical task, full fine-tuning, adjusting all parameters, is also an option. Additionally, the paper mentions another interesting technique here, knowledge distillation.
Knowledge distillation, what's that?
This is where you train the smaller, specialist SLM to specifically mimic the outputs generated by the original, more powerful generalist LLM on your task-specific dataset. The SLM learns to act like the LLM for that narrow task. This can be a clever way to transfer some of the more subtle, nuanced capabilities or response styles from the LLM down to the smaller model. It's almost like the SLM is serving an apprenticeship under the LLM for that specific job.
Huh, that's clever. So the SLM learns directly from the LLM's successful examples for that task. And I guess this whole process isn't just a one-time thing, right? AI models drift, user needs change. It sounds like continuous improvement would be key.
Absolutely not one and done. The final step, S6, is iteration and refinement. You need to periodically retrain the specialized SLMs with new data that's continually being collected, back to step S1. And crucially, you also need to train and update a router model.
A router model, what does that do?
The router model is a small, efficient model whose job is simply to look at an incoming internal request within the agent and decide which specialized SLM, or maybe the original LLM, if no SLM is suitable, is the best one to handle that specific request. It directs traffic.
Ah, okay, like a dispatcher.
Exactly like a dispatcher. Periodically retraining both the specialist SLMs and this router model with new data is essential to maintain high performance, adapt to evolving usage patterns or new tasks, and ensure the whole system remains optimal over time. This creates that continuous improvement loop we talked about. It can lead back to step S2 for more data curation, or maybe even step S4 if a brand new, better SLM becomes available for one of your tasks. It's designed as a self-improving system, constantly getting better and more efficient as it's used.
That conversion algorithm sounds incredibly practical and well thought out. Okay, to further solidify their argument about the potential here, the paper provides a few case studies. They actually estimated the potential extent of this LLM to SLM replacement in a few selected popular open source agent frameworks. Let's look at the first one they mentioned, MetaGPT. What is MetaGPT, and how much of its LLM usage did they estimate could potentially be handled by SLM?
Right, MetaGPT. It's an Apache 2.0 licensed framework, and it's quite ambitious. It's designed as a multi-agent system that basically emulates an entire virtual software
A
company.
whole company.
Yeah, it assigns different roles to different agents, like a product manager agent, an architect agent, an engineer agent, a QA engineer agent. These agents then collaboratively handle software development tasks all the way from drafting initial requirements and designing the system architecture through to writing the code, testing it, and documenting it. It aims to be an end-to-end software development simulation using agents.
Wow, okay. That's a very comprehensive multi-role agent system. How does it typically use LLMs to power all those different functions? What kind of LLM invocations does it make?
Its LLM invocations are quite varied.
Mhm.
It uses them for role-based actions where each specialized agent role, like the engineer, invokes LLMs to fulfill its specific responsibilities, such as writing code snippets or generating documentation based on the architect's design. It uses structured prompt templates quite heavily to try and get consistent outputs from the LLM. It also relies on the LLM for more dynamic intelligence, things like planning the overall project, reasoning about design trade-offs, and adapting the plan if issues arise. And it incorporates retrieval-augmented generation, or RE.
Ori again. Remind us what that is.
That's the technique where the agent first pulls relevant information or context from a large external database or document store, then provides that retrieved information to the LLM along with the prompt. This helps the LLM generate a more informed, accurate, and contextually relevant response. MetaGPT uses this for things like accessing existing code bases or technical documentation.
Okay, so it's using LLMs for a wide range of tasks, from coding to planning to documentation. Given all that variety, how well suited did the paper find SLMs to be for replacing MetaGPT's LLM queries? Does it require that broad general intelligence everywhere, or are there enough repetitive subtasks?
They found a mix. For MetaGPT, SLMs would be very well suited for many of the routine code generation tasks, especially generating boilerplate code or implementing fairly standard functions based on clear specifications. They'd also be good at producing structured responses based on those predefined templates MetaGPT uses. These are the more repetitive, predictable subtasks where a smaller, specialized model could handle the load beautifully and efficiently.
But not for everything.
Not for everything out of the box. The paper notes that SLMs would likely require further fine-tuning using data gathered through that conversion algorithm to reliably perform more complex tasks. Things like high-level architectural reasoning, adaptive planning when the project hits unexpected roadblocks, or complex debugging these initially benefit more from the broader contextual understanding and general reasoning capabilities of a powerful LLM.
Okay. So considering that mix, what was their final estimate? What percentage of MetaGPT's LLM queries did they think could be reliably handled by specialized SLMs, perhaps after some fine-tuning?
Despite those limitations for the most complex tasks, their conclusion for MetaGPT was that approximately 60% of its current LLM queries could likely be reliably handled by appropriately specialized SLMs.
60%. That's really substantial. More than half of the LLM workload could potentially be offloaded. Okay, let's move on to the second case study, Open Operator. What's its main purpose?
Open Operator is an MIT licensed framework focused on workflow automation. Its purpose is to let users define behaviors for agents that can perform tasks involving things like making API calls to external services, monitoring systems, and orchestrating sequences of actions across different tools and services. Think of it as a kind of digital assistant specifically for automating business processes or IT operations.
Okay, workflow automation. And how does Open Operator typically use LLMs in its day-to-day operations? What are the key LLM-driven functions?
It primarily uses LLMs for three main things. One, natural language processing, to understand user intent expressed in natural language commands. For example, summarize today's sales reports and email them to the team. Two, decision-making, to help guide the execution flow of the automation, perhaps deciding which tool to use next based on the current state or the user's goal. Three, content generation, for tasks like writing summaries, generating reports based on the workflow's outcome, or maybe composing notification messages.
Given those uses, understanding language, making decisions, generating text, how much SLM replacement potential did they estimate for Open Operator? Was it as high as MetaGPT?
For Open Operator, the assessment was a bit different. SLMs would be well suited for the simpler tasks, like basic command parsing and routing if the commands are fairly structured, or generating simple messages based on predefined templates. These are relatively straightforward, constrained NLP tasks. However, the paper points out that SLMs would likely hit limitations when dealing with more complex requirements. Things like multi-step reasoning needed for complex decision-making within the workflow, or maintaining coherent conversation flow and context if the interaction with the user becomes more extended or nuanced. These are areas where the broader contextual understanding of LLMs would likely continue to offer significant advantages.
So a lower potential for replacement here.
Yes. Therefore, the estimate for Open Operator was lower than for MetaGPT. They concluded that about 40% of its current LLM queries could likely be reliably handled by appropriately specialized SLMs.
40%. Okay, still a very significant chunk, even if it's less than MetaGPT. It shows there's still substantial room for optimization even in NLP-heavy agents. Finally, let's look at the third case study, Cradle. What is Cradle designed to do? This one sounded quite cutting edge from the outline.
Cradle is indeed quite advanced. It's another MIT licensed agent framework, but it's designed for something called General Computer Control, or GCC.
General Computer Control.
Yeah, basically it enables AI agents to operate graphical user interface, GUI applications directly. It works by taking screenshots of the computer screen as input and then simulating user interactions like mouse clicks and keyboard inputs. Think of it as an agent that can literally see your screen and click on buttons or type into text fields, automating tasks within almost any standard GUI application, even if it doesn't have an API.
Wow, that's like giving AI eyes and hands to use regular software. That's an incredibly advanced capability. How does it use LLMs for this? It sounds like it would require a lot of visual understanding and complex planning.
It does rely heavily on LLMs for the smarts. Cradle's LLM invocations include interface interpretation, analyzing the screenshot to understand the layout, identify buttons, text fields, icons, etc., task execution planning, planning the sequence of GUI actions, clicks, typing, needed to complete a user-requested task within that application, error handling, diagnosing problems when the application doesn't respond as expected, e.g. an error message pops up, and trying to figure out how to recover or replan. It's essentially using the LLM's multimodal understanding, interpreting the image of the screen, and its reasoning abilities to decide what to see and what to do next on the GUI.
Okay, that sounds very LLM intensive. How did SLM stack up for these kinds of tasks? It seems like understanding novel GUIs and planning complex interactions would require a lot of general world knowledge and reasoning.
Again, it was a mix. The assessment found that SLMs would actually be quite well suited for handling repetitive GUI interaction workflows. If an agent needs to perform the same sequence of clicks and data entry in a specific application over and over, an SLM could be fine-tuned to manage that sequence very efficiently. It could also handle the execution of pre-learned click sequences quite well.
So good for routine GUI automation. Where would they struggle?
They would likely face challenges with tasks that require more dynamic adaptation. For example, if the GUI layout changes significantly due to an update, or if the agent needs to handle completely novel, unstructured error messages or situations it hasn't been specifically trained on. These scenarios require a higher degree of contextual understanding, visual reasoning, and generalization that LLMs typically provide more readily.
Right, adapting to the unexpected is harder. So given that trade-off, what was the final estimated replacement potential for Gradle?
Despite these challenges with dynamic adaptation and novel error handling, the paper's conclusion for Cradle was surprisingly high. They estimated that approximately 70% of its current LLM queries could likely be reliably handled by specialized SLMs, especially for automating well-defined, repetitive GUI tasks.
70%. Wow, that's the highest percentage of the 3 case studies. That's fascinating, especially for such a complex task like GUI control. What are the overall implications we should take away from these varying percentages? 60%, 40%, 70%. It sounds like even in systems explicitly designed around powerful LLMs, there's still a huge amount of room for optimization using SLMs.
That's exactly the key takeaway. These varying percentages are critical because they demonstrate empirically that even in complex agentic systems that were originally designed around and heavily reliant on state-of-the-art LLMs, a significant portion of the actual language model workload could still potentially be offloaded to more efficient, specialized SLMs.
This isn't necessarily about completely replacing LLMs everywhere overnight. It's about intelligently segmenting the workloads. It's about using the right tool for the right job within the agent's internal processes. Even a partial shift towards SLMs for the more routine, high-volume tasks, as indicated by these case studies, points towards a profound potential for improving operational efficiency and reducing costs across the entire agentic AI industry. It strongly underscores the paper's core argument. The actual level of intelligence needed for many agentic subtasks is already achievable with today's smaller, more specialized models, making them a highly practical, cost-effective, and agile alternative for building the future of agentic AI.
So wrapping this all up, what does this really mean? This deep dive into this NVIDIA and Georgia Tech paper, Small Language Models Are the Future of Agentic AI, it really reveals a powerful, well-reasoned argument. It strongly suggests that small language models, SLMs, through their specialized capabilities, their compelling economic efficiency, and their inherent operational suitability for many agent tasks, aren't just some niche alternative to LLMs. They are potentially the necessary future for building truly scalable, sustainable, and economically viable agentic AI.
And what's really fascinating here, I think, is that the paper doesn't just stop at making a prediction or presenting a compelling theoretical argument. It goes further and offers a concrete, actionable path forward. It meticulously outlines that 6-step algorithm for how developers can actually convert existing LLM-centric agents to a more sustainable, cost-effective, and ultimately more efficient SLM-first architecture. It really challenges us as a community involved in building and deploying AI to look beyond the undeniable hype surrounding sheer model size, and instead critically consider where true value, operational efficiency, and responsible resource deployment actually lie when we build these practical AI systems.
Absolutely. And the authors themselves, they explicitly call for more discussion on the effective use of AI resources and concerted efforts to lower the cost of AI across the board. This brings us to a final important question for you, our listener, to really consider. If this proposed shift to SLMs truly takes hold, if it gains momentum, what could that really mean? What are the downstream implications if AI becomes not just incredibly powerful, but also significantly cheaper, far more adaptable to specific needs, and maybe even more widely accessible, running directly on our own devices? How might that change the way AI agents integrate into our daily lives, our workplaces, our industries? Think about the possibilities that open up if AI becomes not just a tool for large corporations or researchers, but something that truly empowers everyone, everywhere, in new, incredibly personalized, and perhaps more private ways. Thank you for joining us on this deep dive.